Well, as we ended our last video, we were talking about sketching a digraph from that matrix there, the adjacency matrix. I've gone ahead and done that here, so you can compare that with whatever you did. You might notice that for this one here, the C and E edge, I went ahead and looped it around. Your edges don't have to be straight lines, just so as to avoid drawing edges over edges if you don't have to. And so that corresponded to this number one here that goes from C to E, and this number one here that goes from E to C. So that's this direction for the last one there, E to C. So kind of a fun question maybe to ask, what will the adjacency matrix look like for some of our particular types of graphs that we've discussed, like PN or CN or KN, and you can think about that. I'm going to leave most of that for you to think about, but maybe we'll look at PN. So PN is going to look something like this. This one right here is actually P4, right? That's P4 that goes from V1, V2, V3 to V4 in that way. V1 has degree 1, V2, V3 have degree 2, then V4 has degree 1, just standing that way. So if you draw the adjacency matrix, I'm going to use parentheses here rather than brackets. Sometimes people do that. And we use the natural order here. It's going to go V1 goes to V2, V2 goes to V3, V3 goes to V4, and then V4 goes to V3, and that's all. Now what did I leave out here? Well, V2 also goes to V1, and V3 also goes to V2, like so, right? So that's kind of the way it's going to look like. So all of the rows except the first and the last will have two ones in them, like so, and they'll be going down and to the right, like so, shifted by one each time you go down. But if you go up and it shifts and you lose this one, and as you go down you lose that one when you shift it to the final row. That's just one way to look at it. But again, maybe play around with these, see what those do. This leads us into one of our big topics of isomorphic graphs. And the notion of isomorphism is capturing what are the essential components of a graph, the essential features of a graph. As again we've said, a graph is not determined by a sketch. There are many sketches for a given graph. So we want to know what it is about a graph that distinguishes it from other graphs so that we can compare two graphs and say whether they're really the same or not. So we're going to talk about what does it mean for two graphs to be essentially the same, even though they may actually have different points for vertices. What makes them the same? And this is the notion of isomorphism, or same form, from the Greek for same and form. So we're going to talk about this isomorphic idea. We'll say that two simple graphs, and now I'm just going to do it for simple, so I've emphasized that here. G1 that has a given vertex set V1 and edge set E1, and G2 in the like fashion, are isomorphic. They're isomorphic with an IC there, and we'll write it with a little double squiggle there. If there is a one-to-one matching of the vertex set V1 and V2, such that vertices that are adjacent in G1, let me rephrase that, vertices are adjacent in G1 if and only if the matching vertices are adjacent in V2, right? So if there's an edge between two vertices in G1 and you have the two corresponding vertices in V2, if there's an edge here, then, and these are corresponding, then there better be an edge there. There has to be an edge there, and vice versa. The one-to-one matching is an isomorphism, okay? Isomorphism for the actual matching. So that isomorphism is really a one-to-one onto function from the one vertex to the other, so that for all u and v, sorry, that should be a lowercase u, in v1, u and v are adjacent if and only if their images, f of u and f of v, are adjacent in G2. Yeah? You have to adjust it slightly for pseudographs where there's multiple edges, but I'm not going to write down that formally. So let me do an example or two to illustrate what goes on. So let me clean the board here a little bit. And I'm going to put down here a couple of graphs. Here's one of them. And I'll label the vertices A, B, C, and D. There's only 4 vertices. That crossing in the middle is not a vertex. So we could move that edge out of the way if we wanted to. So that's G1. And for G2, I'm going to have the graph that looks like this. Okay, a triangle, but we'll drop a perpendicular, so to speak, like so. It doesn't really have to geometrically be perpendicular. Let me label these W, X, Y, and Z. And now, let's see. Are those the same graph? Are they isomorphic in the sense that it's really just a renaming of the vertices and the same edges would persist? It's another way to think about it. And one way to figure out how to match this up is to say, well, if those are the same graph, they've got to have the same number of vertices. Well, sure enough, they're 4 and 4. Same number of edges. If you count them, you'll see both have 5. Yes. And let's see, they've got to match up in the right way. So one way to think about this is that notice that the degrees of these are, there's a 2 and a 2 and a 3 and a 3. And true enough, the 3's are adjacent. Here there's 2 3's, and then there's also 2 2's. So that actually gives some hope here, but that doesn't prove it. What we're going to do instead is actually demonstrate the matching or isomorphism, and this is what I will expect you to do when you're showing me that it's an isomorphism. And in this case here, I think it would be natural to say, well, let's take the degree 3 ones and match them with the degree 3 ones over here. There's quite a bit of symmetry, so it's not going to really matter which way we do that. So what I'm going to do is do the isomorphism. I'll label it that way, isomorphism. Morphism, there's an R missing. So at this stage, we really are only conjecturing that it's an isomorphism, but I'm going to put A, B, C, and D down here. And so I'm going to match up C of degree 3, let's say with W, and D of degree 3 then would have to match up with Y. When you do this, it's nice to have, just for me to be able to read it easily and quickly, it's nice to have the V1 in order, and then the V2 may not be in order. That really helps for me to be able to see what you're doing. It's not really a necessary ingredient, but it makes it easier to work with. So A then and B each have degree 2, and they're both connected to the degree 3 vertices. So X and Y have the same pattern. So I'm just going to match up A with X and B with Y and hope it works out over here. Now, to show this is an actual isomorphism, let's confirm it. So A is adjacent to C. I'm going to check all the adjacencies. Is it true then that X, which corresponds to A, is adjacent to W, which corresponds to C? So that would be X and W. Are X and W adjacent in this graph? Yeah, sure enough they are, so that's okay. So what I have here is adjacent. Is this adjacent in G2? And so A is also adjacent to D, and that would be X, and D matches up with Y. are X and Y adjacent? Sure enough, they are. Good. Okay, so that's all of the adjacencies of A. And then B is adjacent to C, and B is adjacent to D. And let's just check those out. B matches up to Y. So that would be Y. B matches up to, that's not right. B matches up to, that should have been a, what, a Z? Right, a Z. Whoa. How did I do that? We chose A and B to match up with a degree 2 one, so X and Z. So B matches up to Z, so that would be Z. And C we already saw was matching up to W. So our Z and W, yep, Z and W are connected right there. B matches up to D would be Z and Y. And our Z and Y connected. Yeah, Z and Y are connected. So that brings us to C. C matches up to A and B, but we've already dealt with those. So let's go down to C matches up to D, and C matching up to D would be C and D, or W and Y. Do W and Y match up? Well, sure they do. That's this edge right there. So they do match up. And then we already have all three of them with D, so that does it right there. So yes, it is an isomorphism. What is it? The matching. And G1 is isomorphic to G2. Okay? We'll do more of this in the next video.